All right. Today, we are going to be showing and talking about more evidence for the Big Bang. Now, remember, the Big Bang happened 13.7 billion years ago. And so, in order for us to be able to defend that something like that happened 13 billion years ago, we have to find evidence that's around today that says that this expansion of energy happened 13 billion years. And so we're going to go back again to the electromagnetic spectrum that is in our lives, that the universe has all around. And so we are not going to be looking at the visible light spectrum that redshift is focused on, the evidence of redshift. We're going to go to microwaves in order to get more evidence that this idea that the universe started from an expansion of energy happened. So in order to do that, we are going to be looking at this document. This document is cosmic microwave background radiation. Cosmic meaning it's something in space. Microwave for that's the type of energy it is, and it's in the background. It's everywhere in the universe. And energy is just another word. Radiation is just another word for energy. Right. So the first thing we're going to talk about is why do we think that there's radiation in the universe to begin with? And that's because of this idea of the Big Bang, that 13.7 billion years ago, the universe started with an expansion of energy. The universe started with an expansion of the energy, and the energy of today is from that moment in time. Literally, space and time itself were created in that moment. So our goals for this activity are to discover what is responsible for the background radiation found in the universe, and why does this radiation surround us and have the wavelength that it does. Okay, so that's important. We're going to really focus on, why does it have the wavelength that it does? That's what we're going to be looking at. So we're going to do that by looking at a normal balloon, and I'm not expecting you to have a balloon at your house, and so I've got a balloon right here. It's going to be the balloon of science. So we're going to put a small amount of air into the balloon so it's slightly inflated. Okay, and this is going to represent the early universe. So this is a model, and in science we use models all the time in order to help make something more understandable. If it is a large object like the universe, I can't bring the universe into this room. And so we use models a lot in science to gain a better understanding of the world and the universe around us. So now what I'm going to do in my baby universe is I am going to put a transverse wave all the way around the circumference of my universe. Oh, my hand is not working very well. There we go. Oh, and there we go. So I have now a non-mechanical transverse wave. It's transverse because it has peaks and troughs, or crests and troughs. And it's non-mechanical because this wave is traveling through outer space. Okay, this is our universe, our baby universe. Now what it's asking me to do is it's saying use a Sharpie, draw 2 points near the top like this. I'm not going to do that. Instead, I'm going to pick 2 spots on my wave. I'm going to pick 2 little waves. I'm going to put 2 dots there so that I can go ahead and measure. Where is that? Where the heck is it? I'm going to measure between those 2 peaks right there, crest to crest, to see what we're starting out with as far as the wavelength. So I'm going to use my metric ruler, And using metrics, I'm going to go from peak to peak, and I have 0.7 centimeters. 0.7 centimeters. That means I've got 7 millimeters. Okay, that's the length of my wave in my early baby universe model. All right, so now it's saying blow more air into the balloon so that the balloon is inflated to the size of a cantaloupe melon. So I'm going to do that, and it's asking me to pay close attention to the wave. Let's see what happens to my energy. Okay, so as I have expanded my universe larger and larger and larger through time, my wave points have gotten farther away from each other. So what I'm going to do is I'm going to measure that new distance from crest to crest. And now I have a distance of 1 point, it looks like 8. So I've got 1.8 centimeters. That's what is my wavelength. So my wavelength has increased. My wave has gotten longer as my universe has expanded. All right. So here we have some questions. It said, what happened to the physical distance between the 2 points of the line when more air was added to the balloon? And be specific. So what I'm going to first do is describe it in terms of qualitative data. I'm just going to explain and describe what I saw. So I'm going to say the distance between the 2 points, I'm going to say between crest to crest, increased. So that was my qualitative data, just kind of describing what I saw. Now we're going to use quantitative data, measurable data, to explain and defend what I saw. So I'm going to say the distance increased from 0.7 centimeters to 1.8 centimeters. So I'm defending what it was that I said happened. I said that the distance from crest to crest increased, and I'm defending it using quantity, using quantifiable or measurable data. All right, now we're going to draw the wave. It says the wave below describes or represents the wave that you drew on your balloon when it had a small amount of air inside. Draw another wave to show what happened to the wavelength, which is the distance between crest to crest, so from here to here, when you added more air to your balloon. And so I'm going to say that my wavelength, okay, it got bigger. And I'm going to draw my new wavelength so I can show that it got bigger. You're still on that same page. I am not. It says, think about the wave that you drew in number 2. Question number 2. How does the wavelength, the frequency, and the energy of this wave compare to the wave on the balloon before you added air? So if I'm thinking about the wave that I started with, it had a shorter wavelength. So this wave has a longer wavelength. I'm going to say the new wave has a longer wavelength. And if it's got a longer wavelength, if I go back up to this wave, if I look at the frequency, well, if this is the new wavelength, then this wave is not going to fit as many times as this wave can. This wave's got a shorter wavelength. It's more frequent. There are more waves that fit. This has a longer wavelength. It's less frequent. Less waves fit. So I can say that it has a lower or less frequency. longer wavelength, lower or less frequency. Each energy wave or each wave delivers some energy. And so if the wave is less frequent, coming less often, it's delivering less energy. So I'm going to have lower or less energy. So that represents the kind of like the universe we see today. If this model represents the history of the universe, what would happen to the wavelength, the frequency, and the energy of this wave if we went back in time? If this is the model that we have right now of the universe, if we want to reverse this process and see what happened early in the universe, let's deflate the balloon and see if we can figure out, let's see what's happening to our wavelength. We're going back in time. The universe is getting smaller and smaller. The wavelength is getting shorter and shorter. The distance between the crests are getting shorter. More frequency, higher energy. That's what's happening. Okay, that's what we believe happened in the early universe. So we're going to go ahead and talk about the wavelength. The wavelength, as we went back in time, became shorter. As it gets shorter, more waves can fit. So the frequency increased, became more frequent. And if the frequency increased, the energy delivery also increased because each wave delivers energy. All right. The next thing we're going to do is we are going to watch a movie, and it is going to be a short video. It is linked on the website. It is linked on the website. I am going to try to show it now. Hopefully, Canvas picks it up. But if not, then go ahead and click on the link that I have put on Canvas on this day with this lesson so that you can go ahead and watch this. But I am hoping that by me pulling this up, we will be able to watch this video. You'll be able to hear it. This is my favorite astrophysicist. His name is Neil deGrasse Tyson. And he's going to try to explain and tie in what we saw to microwave energy, because we've still not really talked about microwave energy. So we're going to talk about that. I'm going to pause for a minute. All right. So in order for you, we're back now. We're going to take notes. The video, if you could just watch it on your own, that would be great. So pause this and go watch the video that I have about cosmic microwave background radiation with Neil deGrasse Tyson. So that's what I need you to watch. We are then going to take those notes here. So make sure you pause it, watch the video, and then come back and finish these notes. So we're going to talk about the way Neil deGrasse Tyson taught us that we have this energy that was released 13.7 billion years ago. And energy was released in all directions. Energy. Now, energy just wasn't released that way. Energy was released all over. So I'm going to say, let me move my paper over just a little bit. I'm going to say that the energy was sent out in all directions. And we should probably put that this happened 13.7 billion years ago. This represents the Big Bang. So energy was sent out in all directions. Energy was sent out in all directions. as the energy wave moves outward, comma, as the energy wave moves outward, it stretches as the universe grows. I'll say as the universe expands. So, in the beginning, energy was sent out in all directions. As the energy wave moves outward, it stretches as the universe expands. So we're going to show that down here with another pow. And originally, the energy was tiny wavelengths, and then it stretched out through the universe. This again was 13.7 billion years ago, and this is the universe today. We have very short wavelengths here, the shortest wavelengths, and we learned short wavelengths equals high energy. So the early universe had incredible high energy amounts. Universe today, longer wavelengths, comparatively speaking. And so we have lower energy. All right, so how are we tying this into microwave energy? Well, I'm so glad you asked. As Neil deGrasse Tyson told us, when looking at the EM spectrum, the spectrum is just another word for range. This is an electromagnetic range of energies. We have gamma, which is high energy, short wavelengths. And then as it passes through visible light, UV, and it stretches out even more, we're going to end over here with microwaves. Now, I know that there's radio waves on the other side, but we're going to stop at microwaves. And if we look at this high energy, we can think early universe. And as that wave spread out like ripples in a pond, it stretched through the spectrum, moving from one type of energy to another until today, we have this low energy background of the universe, where everywhere we look, we see this microwave energy. It's the cosmic, meaning in space. It's in the background. It's microwave energy or microwave radiation. So as the initial expansion, from the Big Bang spreads out, comma, as the initial expansion from the Big Bang spreads out, the universe cools. Right, over time, it's been 13.7 billion years. The universe cools as the energy lowers. So in this kind of an environment, we're able to finally have atoms form. And then over time, matter is created. Not a lot of time went by here, not a lot of time at all. And then from that matter, now hundreds of thousands of years pass, and you get that matter clumping together and making the first stars. We're going to be talking about that in our next unit. And then over time, those stars coalesce through gravity and make our first galaxies. Definitely not the organized galaxies that we have today, like our Milky Way galaxy, but this first galaxies began to be created. All right. Those are our notes. Again, if you did not watch the Neil deGrasse Tyson, it's like 4 minutes. Watch it. It's a good wrap up. It ties all of this in, and that's pretty much where we are going. So that's going to be that. Let me go ahead and end this.